Coordinate transformation started, I would say, back in the late 70s, early 80s. Okay, predominantly initiated and pioneered by a guy called Joe Thompson at Mississippi State, who's a very famous aerospace engineer. Okay, he came up with the idea of doing coordinate transformations because back in the old days, what happened was people were looking at flow over airfoils. Now, you know, okay, here's an airfoil. Okay, my poor drawing of an airfoil. So you do flow on that. In the old days, what people were doing is, if you had a circle, because there were no mesh generators in those days, remember, okay? This is at a time when, so many of you have been taking CFD classes. Now in CFD, there is this famous algorithm called the simple algorithm, developed by Spalding and Patankar, okay? Used for pressure-based codes. That algorithm was developed in 1972. So if you go back to, so these guys were from Imperial College London. If you go back to that original paper and read it, in fact, just a couple of days ago, I was going over that paper to see what all it has. And the only computation reported there is for a computational domain, which is a square with 16 by 16 mesh. Okay? You're solving Navier-Stokes on a 16 by 16 mesh. That's it. That was groundbreaking in those days. And that paper is, it probably has around, you know, more than 10,000 citations. So that was what was going on in those days, 1972. Around late 70s, people were doing this. You have, let's say, a circle inside a square. Now, how are we going to model this? Okay? So what they would do is, they would basically do stagger step mesh. Okay? Sort of approximate the outline of the circle. I'm not doing a good job here, but let's say you have a curve like that. That would be approximated by a stair step like that. Okay? Which was great for heat transfer applications. If you want to do, let's say, heat conduction in a plate which has a hole cut into it, okay? A stagger step or stair step approximation like that wouldn't give you such, you know, really unacceptable solutions. Fairly decent solutions you would get. But think about doing that for an airfoil. What would it do to your drag? There's no meaning doing that kind of calculation, okay, with a stair step mesh. It's pointless. So that's when Joe Thompson, who was obviously an aerospace engineer, he realized we got to do something that fits the mesh to the body. Otherwise, we have no hope of calculating drag on airfoils. Okay, and that's when all this activity started, and he put together a project including a bunch of universities and research institutions called the National Grid Project. And people started working on structured body-fitted mesh generation using coordinate transformation and solving PDEs using coordinate transformation. So this started way back in the late 70s, early 80s. Unstructured finite volume came mid-90s, late 90s, okay, much later, when finite elements had in the meantime really developed and mesh generation became, you know, a huge area, and people were generating meshes out of full cars by then. Okay, so this is that's a little bit of the history. So here's the idea that basically what you're trying to do is you are trying to map this onto that. Okay, it's kind of like, the best way to think of it is, if I take a square piece of paper and I want to model some other object of some other shape, okay, think of this paper as, let's say, made out of Play-Doh. Okay, all you do is you draw the outline of that new object you want to model and then kind of pull at its edges, okay, and make it exactly conform to that shape. So what will happen is, if you now draw a bunch of grid lines on this, those grid lines will also get distorted and stretched, and you will basically have a body-fitted mesh. That's the whole idea. Okay? So this is what we are trying to do. Now, just for your information, this vector set, unit vector that I've shown here, these guys, xi1, xi2, xi3, these are called covariant basis vectors. Okay? Covariant basis vectors, the definition is that they are tangential to these, you see these curves? So they are locally tangents to those curves. Okay. Instead, you could have a vector where, for example, this guy, instead of being a tangent to that curve, is actually the local normal to this plane. Okay. That is known as a contravariant basis vector set. Okay. Typically, people use the covariant basis vector sets for reasons which has to do with fluid flow calculations. It kind of basically gives you the normal flux at a phase very easily. If you use contravariant basis vectors, then that will be very problematic. Okay, but either one can be used. People prefer the covariant basis vectors. So the idea is this, as I said, this is what we are trying to do. We take a square in 2D. This is a 2D example, but you can think of it in 3D also. You take a square and you map onto a different shape. Okay? And so your constant I lines, constant J lines, they remain as is, except that they get distorted. Okay? And X and Y, sometimes we call it just X1 and X2 for generality, becomes Xi1 and Xi2. Okay? So Xi1 and Xi2 are your two transformed independent coordinate systems. So mathematically, this is what we are trying to do. We are trying to transform x1, x2, x3 to xi1, xi2, xi3. All right? So this guy here, so in general, I can say x1 is a function of xi1, xi2, xi3, x2 is a function of xi1, xi2, xi3, and x3 is a function of xi1, xi2, xi3. Okay? And this is known as the forward transformation. Now here I've just written it in functional form, but I'll give you some examples soon. Okay, the backward transformation would be the reverse, where you write xi1 in terms of x1, x2, x3, and so on. All right. So this is known as the forward transformation. This is known as the backward transformation. In most cases, the forward transformation can be written in explicit form, and this is a very important realization. Okay. For example, if we were to transform from Cartesian to spherical coordinates, here are our formulas. We know that. Okay? But now think about expressing theta or psi in terms of x, y, z. You can't do that. It's an implicit relationship. Okay? This here is an explicit relationship. The reverse is not an explicit relationship. It's an implicit nonlinear relationship. Okay? Very complicated. So I cannot write psi in terms of x, y, z, the nice expression. Okay. In some cases it may be possible, but in general it's difficult. So the backward transformation is difficult to write explicitly. The forward transformation is usually the one that's known. All right. Any questions so far? All right. So the question now is, what we are trying to do is, in PDEs we have partial derivatives. For example, something like this. Okay. Now here I am using x1, x2, x3, but they're really your x, y, z Cartesian coordinates. Okay. So we want to express this guy in terms of these kinds of derivatives. Okay. Derivatives in terms of the transformed coordinates. All right. So that's our goal. Now, obviously, we can use our chain rules of calculus to write those relationships. So this is just taking this expression here and then applying the chain rule of calculus to come up with, for example, dphi dx1, dphi dx2, dphi dx3. Okay. The reason I'm deriving these are the kinds of derivatives that will show up in my partial differential equation. Okay. So we can write that in matrix form in a very neat manner, and this is what it would look like. All right. So you can see I have d psi dx1 times that, which is your first term, then d psi 2 dx1 times that, which is your second term, and so on. And then this guy times that, which is your third term. So it's row by column multiplication. All right. This is known as the Jacobian of the backward transformation. Okay. Why backward transformation? Because it's expressing psi1, psi2, psi3 in terms of x1, x2, x3 rather than x1, x2, x3 in terms of psi1, psi2, psi3. That's what these derivatives are telling me. How much does psi1 change with respect to x1, not how much does x1 change with respect to psi1. Okay, so this is the Jacobian of the backward transformation. All right. These guys, these partial derivatives, are often known as the metrics of transformation. That's just terminology there. So, as I said, the backward transformation cannot always be written in explicit form. So, therefore, we cannot calculate these partial derivatives easily. Okay. So, for example, if I go back to this here, if I asked you to calculate, tell me what is d psi dx, that's very difficult to do. Okay. So we have to find a way to mitigate that problem. Okay. And to make that possible, what we do is we start with the forward transformation. So we start with the forward transformation, and we again apply the chain rule. Okay. So if I have that relationship, I can say dx1 is dx1 d psi 1 times d psi 1 plus dx1 d psi 2 times d psi 2, and so on. Okay, 3 terms. And what I have used here in the last here is what's known as tensor notations. How many of you are familiar with tensor notations? Okay, so some of you, those who have taken turbulence classes, you probably are. Okay, so all this is it's like this. So if I say AI BI in tensor notations, it means summation from I equal to 1 to 3 AI BI. It's just that you don't write the summation. So anytime you have a repeated index, that indicates a summation. Okay. So the fact that I have this repeated index here, I and I, basically it means partial x1 partial psi 1 times d psi 1 plus partial x1 partial psi 2 times d psi 2 partial x1 partial d psi 3 times dx d psi 3. Okay, that's what it means. It's basically this summation is implicit. We are not writing it out. Okay, so that's how these repeated indices work in tensor notations. Okay, so you see the same thing show up in all of these terms. This one, this one, this one. So 3 terms. I've just written it in compact form as 1 term. All right. Okay, so those are my 3 expressions. Now what we can do is from the backward transformation we can write similar expressions. So here I have written dx1 in terms of that, but I can do the reverse and then write d psi 1 in terms of the partial derivatives in x. Okay, so exact same expressions derived from the backward transformation. All right. Now what we're going to do is so here you see this is tensor notation, right? So this guy actually has x1 x1 plus x2 x2 plus x3 x3, 3 terms really. Okay, I'm going to plug in this guy, these 3 in there in that summation. Instead of dx1 dx2 dx3, I'm going to plug in this equation 1 into equation 2. All right. So when I do that, this is what I end up getting. Again, you see these tensor notations, repeated index show up. So this is actually a whole bunch of terms. It's 9 terms. All right. There are 3 terms here, 3 terms here, 3 terms here, 9 terms. It's just written in compact form like that. And now I can use double tensor notation. So I have a repeated j and a repeated I. Okay. So that immediately makes it 3 times 3, 9 terms. All right. So those are just compact ways of writing it. So now what we are going to do is, obviously, as I said, each of these guys have dx1, dx2, dx3, and so forth, right? This one has dx1, dx2, dx3. Same thing here. So what we are doing here is we are going to group these terms. So for example, here on the left hand side I have that. On the right hand side I am going to have some dx1 containing terms from all 3 of these. Okay. Similarly, I'm going to have some dx2 containing terms. Okay. So dx1 will have 3 terms, dx2 will have 3 terms, dx3 will have 3 terms. Okay. If I group them, this is what I end up getting. All right. So basically gathering terms together. Now once we do that, you notice something very interesting. See, this on the left hand side has 1 times dx1. On the right hand side, all of a sudden I have dx1, dx2, dx3. Okay. Now remember, x1, x2, x3 are independent variables. A change in x2 cannot be written as a change in x1. It's by definition invalid. Okay. If I say something changes in y, I cannot say that can be expressed by some change in x. Impossible. Okay. So if I look at this expression, the only way that can be satisfied is if this is equal to 1 and these guys are equal to 0. Okay. Then basically I get dx1 is equal to dx1. Otherwise it's impossible to satisfy that equation. Okay. So that's what you end up getting. You get the first term equal to 1 and then the next two terms equal to 0, and that happens for all three equations. Okay. So now with those three equations, if I rearrange them, so these three equations, if I write it in matrix form, again notice this is a tensor summation. Okay, so this is actually 3 terms equal to 1. This is 3 terms equal to 0. All right. So if you write it in matrix form, this is what it looks like. All right. So this is the identity matrix, which obviously has 1s in its diagonals and then 0s everywhere else, which come out of this nice form that you see here: 1s in the diagonals, 0s everywhere else. Okay, that's what that represents. This is your Jacobian of backward transformation that we said we cannot calculate very easily because the relationships are often implicit. This is your Jacobian of forward transformation, which we can calculate easily because the relationships are explicit. Okay, so J is, so I'm saying that this Jacobian of backward transformation is J inverse, where J is the Jacobian of the forward transformation. That's this guy. Okay, so this guy is nothing but J inverse because the right hand side has an identity matrix. Okay, so therefore, going back to my equation here, okay, so this said that this is equal to the Jacobian of the backward transformation times that. Now the Jacobian of the backward transformation is the inverse of the forward transformation. Okay, that red matrix is this guy. So therefore we now have this. So we have now fulfilled the goal of writing the partial derivatives in Cartesian coordinates in terms of partial derivatives in the transformed or curvilinear coordinates. Okay, as long as we know how to calculate the Jacobian. Okay, but you know, from the example that I showed you in cylindrical or polar coordinates, it's very easy to do most of the time. Okay, we'll talk about that more when we actually get to finite differences. So, all right, so this is what we where we ended last time. So the idea being that we are trying to express partial derivatives of phi in terms of the Cartesian coordinates x1, x2, x3. Okay, we are trying to express that now in terms of our curvilinear coordinates xi1, xi2, xi3. Okay, and this is what we derived in the last class, that these derivatives can be expressed as the product of what's called the inverse of the Jacobian of forward transformation times the partial derivatives in curvilinear coordinates. Okay. So this is where we had stopped last time. Next task is to figure out how we get the inverse of this Jacobian. Okay, now remember this is the Jacobian of the forward transformation. Okay. So the good news, of course, is that this J is a 3x3 matrix at most, because we are looking at transformation in space. So our space is 3-dimensional at most, and in 2D, of course, it's a 2x2 matrix. So therefore, to calculate the J inverse, we can directly apply the Cramer's rule and simplify everything analytically rather than having to compute it numerically. Okay. That's the whole idea. So here's just a refresher of Cramer's rule. Suppose we have a matrix K which is J inverse. Okay, so here is how we find the inverse. Okay, for those of you who have completely forgotten your high school algebra. So what you do is, suppose I want to find K11, okay, the first element of the K matrix. What I do is I take the J matrix, I strike out row number 1 and column number 1, okay, and I'm left with this part here. Okay, so my inverse K11 becomes the determinant of that part, the 2 by 2 matrix, that guy, okay, as you can see here, divided by the determinant of the whole matrix, the whole J matrix, okay, and then in front you have this coefficient which says minus 1 to the power 1 plus 1, okay. This is actually, in general, it's minus 1 to the power I plus j, okay. So what that means is this. So suppose I am at row at that position 1 1, okay. So this is 1 plus 1, which gives me a 2. So minus 1 to the power 2 is plus 1. So what that means is I have a plus sign here. Then when I move over here, I'm going to get 1 plus 2. This will become negative, okay, and this will become positive again, and so on. Here I have a negative, here I have a positive. So the plus and minus signs alternate. That's what that minus 1 to the power I plus j means, okay. So when you are computing the element or the inverse, not only do you have to take the determinant of that 2 by 2 matrix after you cross off the row and column, you also have to take the appropriate sign into account, and the sign will be given by minus 1 to the power I plus j, okay. So now this matrix here, this numerator here, well, actually the numerator including, you know, the sign, is known as beta. I've written it as beta 1 1. That beta is often known as the cofactor matrix, okay. So the Cramer's rule says that the inverse is just the cofactor divided by the determinant, okay. Any questions? So therefore, instead of writing this is equal to J inverse times that, I can write it directly using Cramer's rule as beta ij divided by j, where j is now the determinant of the matrix J, okay. So this denominator here, as you can see, I've denoted it by j. So that's what my expression becomes. So this equation here that I had on the previous page, this guy, essentially reduces to, in compact form, that equation right there. Okay. Now notice one thing here. There is a j here and the j here. All right. So therefore, what we have there is, on the right hand side, is a summation of 3 terms, because it's a tensor summation. So this basically means if I want to calculate d phi dxi, I'm going to get beta I1 divided by j d phi d xi1, beta I2 divided by j d phi d xi2, and then beta I3 over j d phi d xi3. Okay, because the reason for that is, if you look here, this guy is a square matrix. So when I do a matrix vector multiplication, I'm going to get 3 terms. Okay, I'm going to get the top row divided times that column to get this first element. So it's 3 terms. All right. So keep that in mind. It may look simple when I write it this way in compact form, but actually it's a sum over 3 terms. Okay. So what that essentially is saying is that the partial derivative with respect to x, y, or z is now a combination of the partial derivatives in all 3 curvilinear coordinates. Okay, they get mixed up in a sense. All right. Okay. So now our job is to take that transformation and transform our Poisson equation. So we just found out what the transformation relationship is for the first derivative. Now we are going to apply that to our Poisson equation This is our Poisson equation in 3D. Okay, and again I'm using tensor summation here, writing it as ddxi of dphi dxi. Okay, again notice this is a summation, tensor summation, repeated index, and that's what basically gives you these three terms. All right, so that's a compact way of writing it. We already have this relationship, we have derived this already. Okay, so what I can do is I can plug that in here directly for dphi dxi. Okay, now another way of writing this relationship is as follows. Okay, now I'm not showing the derivation here. The derivation is actually pretty lengthy. One can do it reasonably within about 1 or 2 pages in 2D, but for 3D it gets pretty lengthy to show that you can actually take this cofactor beta ij and put it inside the derivative here. Okay, but that's what it comes out to be once you go through the derivation. Okay, so I'm not showing the derivation here. You have to take me for my word there that this is an alternative way of writing that. Okay, sticking the beta inside the derivative. All right, so what we are going to do now is we are going to use this expression for this inner derivative here, and we are going to use this expression for the outer part. Okay, now what this means is, I mean, you can think of this quantity within brackets as some other quantity psi, let's say. So instead of d phi dxi, we can think of this as d psi dxi. Okay, or you can just think of this as an operator. Let me just write this down. And so this, you can think of this as an operator. Okay, that's what we are using here. So ultimately, when you plug that all in, this quantity here, okay, this part here we have plugged in for that, so that's that guy. Okay, and then the 1 over j stays put for the outer part. So now we are going to transform that part. I have a 1 over j, and you have to be a little careful here, because what happens is, you know, there are two tensor summations going on here. One for the first derivative, which is this repeated index j, and then there is also a repeated index when we get to the second derivative. Notice that here I have a I, and here I also have a I. Okay, so you have to be careful there, because what essentially happens is this becomes now a summation also. So I've switched the index from I to k, okay, because we are using ik here instead of ij. Okay, so you kind of have to think of this as this expression that I have here. I could write this as d phi dxk is equal to 1 over j sorry, it gets difficult for me to write once the pen goes close to the edge. You can think of it as that. So instead of I, I'm using k, okay, in this expression here. So now you take that and then use it here, okay, and again, instead of I, think of this as k to begin with, then you get essentially that expression, right? So moving on, this is our Poisson equation in curvilinear coordinates. Okay, it looks compact, but there's a lot going on here. For one, you see there's j index repeated, there is I index repeated, and then there is k index repeated. So all kinds of summations going on if you start thinking about it now. Okay, so first of all, let's think about this quantity here, this inner quantity. Okay, now beta ik is a 2 by 2 matrix. So this is a 2 by 2 matrix times beta ij, which is another 2 by 2 matrix. So this is nothing but basically we have the beta matrix, beta 1 1, beta 1 2, and so on. Okay, or sorry, 3 by 3 matrix in general. Okay, so this is what we are looking at. Product of two 3 by 3 matrices. So if you think about this, this is a repeated index in I. So what do we have? We basically have a summation over I. So this really represents, if I really expanded it out and wrote it. So if I perform that summation, what will be the indices that will be left over? You're summing over I, right? So what are the indices that will be left over? J and K. Okay? Because what this represents is that you're doing beta 1K times beta 1J plus beta 2K times beta 2J and so on. That's what this really means. Notice that this final answer has no dependence on I anymore. It has only dependence on J and K. Okay? So the final answer is going to be some other matrix. If we call that B, it will have index J and K. It's a product of two 3 by 3 matrices. All right? So you have to remember, anytime suppose I have a multiplication like this, AI times Bij, tensor notation. Okay, what's the final answer going to be? If I write this as C, what's going to be the index of C? Anyone? Cj. Okay, I'm summing over I here. This is nothing but saying summation from I going from 1 to 3 AI Bij. This is what I have written here is basically like a matrix vector multiplication. All right, so that gives me Cj. So for each value of j, I'm going to multiply over all 3 components of I. And so it's going to give me a value depending on the value of j, but I is multiplied through. Okay, so same idea here. This is of course 2 matrices getting multiplied. And so once you multiply through the I, what you end up getting is J and K, sorry, in this case. All right. So let me just wipe out all that so we can see what's going on here. Any questions on that? Okay. So that's what I'm saying here. We are denoting that new matrix, the product of those two 3 by 3 matrices, as some other tensor. Okay, sometimes people call these tensors instead of vectors because they're matrices really, 3 by 3. A vector you think of as a column matrix. Okay, this is 3 column matrices side by side, so it's a tensor. Okay, so this tensor is the product of those two, and if you expand it out, that's what it becomes. Okay, summation over 3 terms. So now if I expand this out, so this becomes my B. Okay, and now if you expand it out, you notice that I have a repeated index in J here and then a repeated index in K here. Okay, so if I look at the inner one, so I have a repeated index in J, so therefore I go B11, B21, B31, okay, and then sum that up, and then I have the repeated index in K outside, so that gives me 3 derivatives, xi1, xi2, xi3, when I go over K. So ultimately I end up getting 9 terms. Okay, so your normal Poisson equation in Cartesian coordinates had 3 terms. The 3 second derivatives. Okay. Now after you transform it, you end up getting 9 terms, because each term now depends on 3 derivatives in curvilinear coordinates. Okay? Any questions? So this is what it looks like after you expand it out and transform, write it in curvilinear coordinates. Okay, now we'll do an example so things will become more clear in a little bit. Okay, but that's the general equation in curvilinear coordinates. Okay, so I've just rewritten it here. Points to note: 9 terms in 3D, 4 in 2D. Okay, so in 2D, many of the terms will go away, as you will see in the example. And then the most important thing to note is these cross derivatives. Notice that now I have xi1 here, xi2 here, xi3 here. Okay, when you had Cartesian coordinates, you only had xi1 square or x1 square, x2 square, and x3 square. There was no partial square phi, partial x1, partial x2. No cross derivatives at all. But now we end up with those cross derivatives. Okay. So the first issue produces more terms than and that, more terms that we have to discretize, which is of course painful. Okay. Already we're struggling with 3 terms. Now we have 9 terms. Second issue makes the discretization process very difficult, because as you will see, when we did Taylor series expansions, we like to do one-dimensional Taylor series expansions. Okay, we don't like to do 2-dimensional Taylor series expansions. But now we have cross derivatives, so what do we do? Okay, so that becomes a challenge. So let's look at an example which sort of clarifies some of these issues and you understand the equations better. Okay, but before I start that, any questions? Okay. So here is the example we are going to solve. You know this already. So it's a 60-degree rhombus. I've denoted here the Cartesian coordinates x1, x2, and then your curvilinear coordinates xi1, xi2. Now, of course, in this case, xi1 is aligned with x1, okay, but xi2 is not, obviously. And then xi1 and xi2 are not even at 90 degrees, as you can see. Okay, these are the boundary conditions. So zeros all around, and then 1 at the bottom. Okay, and I have drawn a stencil for finite difference here, as you can see, denoted by north, south, east, west, but I've also denoted northeast, northwest, southwest, and southeast, and you will see soon that those will be required for the discretization. Okay, so objective is to solve it on a unit rhombus with Dirichlet boundary conditions on all sides. Governing equation, if I just take this equation here, you see the xi3 terms will go away because it's 2D, and then this entire term will go away because this is the xi3. Okay, so I'm left with basically 4 terms. Normally for the Cartesian coordinates I'd have 2 terms. Now I have 4. Okay, 2 by 2 essentially. So that's my equation. All right. So now my job is to figure out the j's, the b's, all these quantities, so that I can simplify the equation further. Okay. Now in this case, it's possible to do it on paper nicely because these lines are not curving, so the j's and b's are not changing locally. Okay. But if you had a very complex shape where the grid lines are curving, then you can't compute them, or you cannot determine them a priori on paper and then put it into your equation. They will change locally and you have to compute them locally. I'll talk about that after I've finished with this example. Okay. So here is our forward transformation in this case. x1 in terms of xi1, xi2, x2 requires only xi2. Okay, that's straight from the geometry. Basically you can see the y component of any point will be xi2 times sine of theta, that length, okay, and then this one will be xi2 cosine theta plus xi1. All right, so pretty straightforward. So I can calculate my Jacobian of the forward transformation. So those are those 4 partial derivatives. You can differentiate these guys with respect to each other. And you clearly see here I get 1 cosine theta, 0, and sine theta. Okay, so straightforward calculation of the partial derivatives. And this is where you see already that the metrics of transformation are independent of anything else. They're constant numbers. Okay, and that's because of the shape of this body. It's, these, as I said, the lines are not curving. They're fixed orientation. Okay, and then the determinant becomes just that times that minus that times that, which gives me a sine theta. Okay, so that's the determinant of your forward transformation. And then your beta 1, 2, so now remember our rule is we take this matrix and from this we figure out the cofactors. This is now 2D. It's very easy. So beta 1, 1, you cross out that, you're left with sine theta. Okay, that's that guy. You don't have a 2 by 2 matrix to deal with anymore. Okay, beta 1, 2, you cross out this, you cross out that, you get a 0. Actually, it's a minus 0 because this guy will have a minus sign in front of it, but it doesn't matter, of course. Okay. Similarly, for beta 2, 1, you cross out this, you cross out that, and like I said, this guy will have a minus sign, so you get a minus theta, minus cosine theta. Okay. And then finally, you cross out that, you're left with 1. Okay. So those are your cofactors. So now your tensor B is given by that. Instead of 3 terms, it has 2 terms. Beta 1k, beta 1j, beta 2k, beta 2j. So I just compute them, okay, with my beta values, and this is what I get. Sine squared theta plus cosine squared theta, which is a 1. And then minus cosine theta for the 2 cross ones, and then again a 1. Okay. So that's my B matrix, or B tensor. I plug it all in. Okay, so this is where your B11 was, and this is your J, this is B21J, and so on. Okay, so all plugged in. All of those quantities are independent of Xi1 and Xi2, so I can simplify this equation considerably, and this is what my transformed equation becomes. Okay. So notice this guy, cross derivative. Okay, you can clearly see if I put cosine theta equal to 90 degrees, cosine of 90 degrees is 0. This cross derivative goes away. I'm back to my Cartesian coordinates, my Laplace equation in Cartesian coordinates. Okay. All right, so starting with that, now I just mentioned this. Now we have to discretize. Okay, so these two guys, pretty straightforward. We already know this. That's your central difference formula. Okay, we've used it hundreds of times by now. So nothing fancy there. So what we are doing here are Taylor series expansions along the Xi1 and Xi2 directions. Okay. Basically, they are independent coordinates, and so we can do Taylor series expansions along those lines. All right, that's what we're doing here. So your delta Xi1 here is basically 1 is the length divided by n minus 1, and delta Xi2 is, again, this is the height, or sorry, the other edge of the rhombus divided by m minus 1. So essentially, again, we are going, this is our rhombus, this is our mesh, looks like that. Okay, you have n nodes in this direction and m nodes in that direction. Okay, so your delta Xi1 is that length, and delta Xi2 is that length. Okay, so cross derivatives, we have to do something special. Okay, so let's start with this guy here. We can write it as that. Okay. That's one of the choices, of course. We could have written with the Xi2 outside and Xi1 inside, but let's say we write it this way. Okay. Now we can approximate that as, so this is d Xi1. So I can say, okay, I'm going to take d phi d Xi2 at the eastern face, or sorry, at the eastern node, minus the western node, divided by twice of that. Okay. So that's what we are doing here. This is kind of like saying, okay, this is another function psi, so I'm doing first derivative of psi, so I take psi east minus psi west divided by 2 delta. Okay, that's what this is. All right. Then the question is, so now we have d phi d xi 2 at the eastern face. So we are seeking derivative in that direction on the eastern face. Okay. So what do? We take this node minus that node divided by that distance for the y derivative. Okay. Again, these are all central difference approximations, as you can see. Okay. They're all second order accurate. So we are taking northeast minus southeast divided by 2 delta xi 2 for this guy. Okay. And then for the on the western face we have the same quantities, so we are taking northwest minus southwest divided by 2 delta xi 2. That's this guy. Okay. You process all that together. Now here I have just written it in terms of the the global index that we have been using. So as you know, this is k plus n, so this will be k plus n plus 1, okay, right there, and this will be k minus n plus 1, okay, so that's that guy, and then this will be k plus n minus 1, and this will be k minus n minus 1, okay. So that's what I've done here. So that's your cross derivative. All right, and let's see what I've done here. Okay, yeah, so I've just written out these two terms separately. Okay, and put them all together into the same equation. So once you put them all together, you see that you have 9 terms now. So I have these standard 5 terms, 1, 2, 3, 4, 5, okay, the north, south, east, west, and the middle, and now I have these extra 2 terms showing up to give me 9 terms, okay. But of course you can use your Jacobi, Gauss-Seidel, ADI, method of steepest descent, central CG, multigrid, any of those methods for this. The only method that you cannot use it directly for is the Stone's method, which we talked about for 5-banded systems. Now, of course, you can rederive the Stone's method for a 9-banded system. Okay, but other than that, any of the methods that you have, you can use to solve that system of equations. Okay. Any questions so far? All right. So here's what the solution looks like. We are familiar with this already on a 41 by 41 mesh. Okay. I think I used the ADI method in this case, but I don't have the convergence curve here. So very similar to the unstructured mesh solution in the previous lecture. Okay. I think this one is slightly more accurate because this is all second order. In the unstructured, remember, the boundary conditions treatment was first order. Okay, but of course, you know, this is not an apples to apples comparison when you compare it to finite volume solutions. So there will be some differences anyway. Okay, but that's what the solution looks like. Any questions before?